Okay, recorder is on. We are streaming to YouTube, and something is kind of odd about my voice. I think it's the placement of the mic or something. But can you guys still hear me? It's just a kind of muffled. Hmm. Let me try to adjust it a little bit. All right. Is that better? Okay. I think the other way was it was touching my neck, so that's why it picked up the voice a little bit differently. Okay. So what we're going to do today is we'll talk about searching in a sorted array. So we'll continue our topic from last last Thursday, when we talked about binary search. Do you guys still vaguely remember that we only need 33 comparisons to confirm that something does not exist in an array of 8 billion items? Okay, very good. Okay, so what we'll do today is to understand the importance of that discussion and a very gentle introduction to what we call time complexity. Question?
Question about how to find the mod of
How to find
the mod of
a mod of something?
it's like
Okay, so let's talk about that first. And that's the homework assignment, right? Yep. And today is the 15th, so I cannot give you the solution of the homework assignment yet, but I can tell you where to find mod. And I think mod is somewhere in top-down design. So we'll,
I give an example. Can you find the mod of it?
huh?
I give you an example.
Well, let's find out, where it is in the notes first, and then see if that is already enough. Because the idea is, I wrote the notes. Why do you think I wrote these notes? So I don't have to talk about it. So if it's missing from the notes, I should go ahead and add it to the notes, right? So we are looking for mod or modulus. Nope. That was never discussed here. Okay, so the first time mod appears was here, but it's not searchable because, okay, so mod was also discussed here, and there we go. Here's mod. So we'll go ahead and read the entire paragraph here. Hopefully that you guys have already read this, because remember, you're supposed to read the modules as we talk about the topics in class, and read ahead of me if it is possible. So this was already in the past, so I'm assuming that all of you have read this already. Although not necessarily the most efficient method, one way is to try out all integers greater than or equal to 2 until we find one that is a factor. Okay, so this is in the context of how do we search or look for a factor given a particular number. Okay, this requires the explanation of the mod operator. A mod b is the remainder of a over b, or a divided by b. Yep.
My question is like the numerator is like greater than denominator. So how to find that?
Sorry?
Like 2/5. How to find the mod of that one? Because it's like do I just like becomes very small?
Okay, so are you talking about 2 mod 5?
Yeah.
Okay, so according to this definition, what is 2 mod 5? No. Okay, so let's try to do some substitution here. You're asking about 2 mod 5. This explanation is about a mod b, right? So a is our 2, b is our 5. Does that make sense? So we are looking for the remainder of a divided by b. So what is the remainder of a divided by b? Okay, so give me a second here. I'm going to get to Zerno. Yes?
Quick question.
Yes, I am indeed recording. Very good. So good reminder there. All right, so this is not for us, okay? So we'll open a new page. All right, there we go. So we have a division, okay? This is how we write the division, yes, okay? And how do we call the part that is under the roof, so to speak? How do we call this part here? What is the English name of that part of a division? It's called a dividend. I know. So this is called a dividend. Sorry? What about the other part? What about the part that is right next to dividend but outside of the house? This part here is called a divisor, right? D-I-V-I-S-O-R. So this is the divisor. And how do we call this part here, which is usually considered a part of the answer of a division? It starts with a Q, quotient. This is our quotient. And typically we use a little r, and then what is the other side? That's our remainder. Okay, very good. What is the relationship between these four things? Yes? Uh-huh. Well, I use a little r, to separate the quotient from the remainder, but I don't know what is the convention in the United States. This is what I did when I was in Hong Kong, so that's the British way of doing it. So what do you guys do in the United States? Huh? Decimal?
Yeah, we don't use like remainders.
You don't use remainder?
No, we just your remainder goes after the decimal. That's what the remainder is.
Oh, okay.
The whole number, that's
Yeah.
the quotient.
Yeah.
That's the quotient, and then the decimal thing after the decimal is your remainder.
Okay, so you don't use a little r to.
1.5. I mean, we use the little. That would just be one remainder.
Okay, let's do one that is kind of obvious, okay? 22 divided by 6, okay? We got a, what is the quotient of 22 divided by 6? How many 6 can I fit into 22? 3. And then how do you write the remainder? Just a number next to it? A decimal? That wouldn't make sense. The remainder is how much? So 3 times 6 is 18, and 22 divided by 18, that doesn't make sense. Okay, it's 6, so how much is left over? 4, okay. So what do you use to separate the quotient and the remainder? Nothing, just a space? I just use an R, okay? 3 with a remainder of 4. Is that okay? So the next question is, what is 2 divided by 5? 2 divided by 5. Okay, let me present this in a different way, okay? I'll present this in the elementary school way, which is basically saying, I got 2 candies in my pocket, and there are 5 students. How many, if I were to distribute the candies as whole candies, how many candies does each student get? 0. Okay. And then the question is, how many candies do I have left in my pocket after I distribute all the candies? I have 2 left in my pocket. You are correct. So does that answer the question? Mod is just looking at the remainder after a division. We toss the quotient away, which is what most people want most of the time, but mod is just keeping the remainder as the answer. Mod is its own operator. Yes?
How would you say that in like qualitative forms? Like,
Huh?
which number would be before the mod and which would be after?
So 2 is the mod. 2 is the mod. So 2 mod 5 is 2. So there, I just finished the first loop for you in the homework assignment. Is that okay? And the quotient is 0, the dividend is 2, the divisor is 5. So those terms are useful because you will use those terms in other classes, not only in math, but also in computer science. Okay, so you have to kind of know what those terms mean in a division. Is that okay? All right. Any other questions related to the homework that is due on Thursday? No questions? Okay, all right. So if the note is not clear, when I try to explain mod this way, you can let me know and I can try my best to change the notes because it's pretty easy to change it or add some explanation to it. But the idea is you have to read the notes because that's where you get all the details. The lecture is kind of more or less a overview or things that I usually do not cover in the notes. Okay. All right, so getting back to the exciting stuff, getting back to binary search. So what I want to do is to present binary search using a spreadsheet. Most of you will probably know by now that I like spreadsheets a lot because they are very useful. All right. Oh, no, too much. All right, so here's a spreadsheet. And this is from the previous class. It illustrates binary search. But what we want to do today is to understand what is time complexity and why do we want to know about time complexity. Okay. So here we go. And we will have array size as one column. And then we'll take one column to say tax time, okay? And then another column for Pat's time. There we go. When the array size is 1, in other words, there's only one element in the array, TAC is using binary search. How many comparisons do I need to confirm that that one thing in the array is not what we want? It will take one comparison, okay? So for now, I'll just write a 1, but then later on, we'll do something about that 1. Pat, on the other hand, is using linear search, which is basically just saying, okay, I'm just going to go through the array from the beginning to the end. So how many comparisons do you think Pat's approach will need to compare in order to confirm that the only thing in the array is not what we're looking for? 1. Very good. Okay. All right. So now we have to take into some consideration, which is a multiplication factor, okay? TAC is using a computer in the early 90s, okay? And many of you were not even born in the early 90s. So I guess it would be unfair to ask you how slow are computers in the early 90s, because that's before your time, right? But what we can do is to make use of Moore's law. How many people have at least heard about Moore's law? Okay, go ahead. Do you want to kind of? Okay, all right. That's okay. Haven't heard of something is still good. Okay, so we'll look it up. Okay, so we'll look it up. Let me close. I don't want to close that. That's still useful. So we'll look up Moore's law. More is the name. Moore's law. And this is Wikipedia's entry on Moore's law. So you can look through it, and so we are talking about a period of 18 months. Okay, now the question is, what is happening within those 18 months? Okay, what is doubling? Okay, so I just point out a word, but what is being doubled? It is the number of components per integrated circuit is doubling. And the idea is that it's doubling every 18 months. So how would that be useful when we need to estimate how fast computers are? How would the number of transistors we can pack into a processor core affect the speed of the computer? It's going to be faster, and it's approximately that. If you double the density of transistors on a processor die, you are approximately doubling the processing speed of the said processor, okay? Which kind of makes sense, right? Because from a simple perspective, let's just say that we're talking about a quad-core processor, because that's all we can fit into a die. versus an octa-core processor, because now we can fit a lot more transistors into the same die. And let's just say that the clock speed are exactly the same, but the memory width is doubled also because of density and whatnot. So would it be difficult to convince you that the quad octa-core processor is approximately has twice the processing power compared to a quad-core processor? So it kind of makes sense, right? Okay, so this is the jump, from using the transistor size or density and translating that into processing speed. So roughly, okay, you can look at Moore's law, and it's kind of saying every 18 months the processor, would double in processing speed. Okay, for the same price. Okay, for the same price, if you bought a $300 processor a year and a half ago, and you buy an equivalent cost processor with inflation adjusted today, the new processor will be about twice as fast as the old other processor that you bought a year and a half. Okay, so we'll use Moore's law in this analysis. And now we want to say, okay, when did Tech got his computer? When he started working with this company. Let's just say it's 1990. Okay, so we'll do this calculation on the side. 1990 is Tech's year, working for this company. And Pat, on the other hand, is a brand spanking new employee. He or she started working in 2019. Okay, so now the question is, if I just use Moore's law as a rough approximation, what is the processing speed change between these 29 years? What do you think? How do you come up with that calculation? Well, we have to find out how many 18 months has passed, right? But that's not too difficult to do, because that is really just this number minus this number. That will give me the number of years, right? How many years do we have how many months do we have per year? 12 months, okay. So we multiply that by 12. So now we can say that, oh, okay, we can kind of estimate, without knowing which month we were hired, we can estimate that there were 348 months between, when Tech got his computer with this company versus when Pat got, Pat's computer, when Pat joined the company. Would that make sense? Yeah. Okay.
Which is multiplied by 2?
No, not yet. Okay, because you have to divide this by 18 first. That will give you the number of periods of 18 months. Okay, because every 18 months it is doubled. So now the question is, what do we do with this number to come up with the factor of speed increase over these 29 years? It's not a multiplication. It is a multiplication, but how do we use this 19.333 number?
I mean, you said every 18 months it gets 2 times faster.
Yes.
And now we figured out those are the period of 18 months. So why wouldn't you multiply it to get to
Because it's a power function thing.
So would you have to multiply it by?
Okay, give you an example. Every 18 months it is doubled, right? So every 36 months it is quadrupled. It's power. It's 2 to the power of. So we are talking about not a small number here, because if you just multiply this by 2, you get about 40-ish, right? Okay? But if you say 2 to the power, this would be close to 1,000,000 times. That is the power of power. Yes, and I did just say that. It is the power of power. Okay? Okay, first of all, let me just run this number first. This is the factor of that increase of power, increase of speed between 1990 and the year 2019. Okay? It is not quite 1,000,000, but in terms of order of magnitude, it's kind of there-ish, okay? So this is basically saying, my computer, or I should say Pat's computer, is 660,561 times as fast as mine. That's a pretty significant factor, okay? So now that we have illustrated the power of power, let me just kind of go a little bit on a tangent, because the father of me is basically talking right now, because I want you guys to understand what is compounding, okay? What is compounding? So let's just say that you're investing money, okay? I know this is a big jump, but bear with me for the time being, okay? So let's say you're investing money. Let's say the interest rate of that investment is 0.5, 0.05, which is 5%, okay? So in 1 year, if you put in $100 into that investment account, in 1 year, what would be the return of that $100? It will be $5, right? Okay, well, that's because power, let's see here, 100, okay, it is 1 plus this amount to the power of 1, which is the 1 year, is 1.05. Okay, so not very surprising, right? What about in 2 years? What is your return in 2 years? Is it going to be 1.1? Okay, so I'm going to multiply this by 100, which is your investment, your initial investment. So you get $105 back. Excuse me, you get $105 in your investment account, where $5 are the interest. Okay, that's your gain. What about the second year? How much money is in your investment account? Is it 110? It is more than 110. Okay? Okay, so I'm going to, let's see. Okay, I'm just going to type this up first. Okay, 1 plus, and then this is the interest, 2 years in this case, and then this is your principal, which is how much money you put in the first place, is $100.25. And you go like, a quarter. I can't do much with a quarter. It is not important, okay? So what we can do now is we can say, this is year 1, this is year 2, this is year 3, and then my equation is now based on, I'm just going to type 1.05 here because that part is not changing, but it's to the power of this number times 100. You go like on the third year, okay, most people would think I will get $115 as my interest, but guess what? You get 76 cents extra because of the power of power, okay? You go like 76 cents. That's not a lot of money. I don't really care about the 76 cents, okay? So we'll keep going like this, okay? I know most of you are young enough where this really should be important, okay? Okay, what about the fourth year? Okay, instead of 120, which is not a power function or compounding, you get $1.55 as the quote-unquote extra because of the power of power. And you say, still not enough to buy a Starbucks coffee. What do I care? Okay? So I'm going to make a bold assumption about the average age of people in this class. Okay, I'm just going to say 20. Okay? You might disagree because it is not your age, but it's just an assumption, okay? And I would assume that you don't need to use this money because you're saving money until you retire, okay? And I would say most people retire at the age of 65-ish, okay? So you have about, 45 years or so to accrue your interest, okay? So we're going to take this and then we'll say, let's check out how much money we'll have in 35 years, 37, 44, and it's 45. So using $100, and using an interest rate of 5% with inflation adjusted, okay? Because inflation also eats away in an exponential way. So with everything adjusted, after 45 years, that $100 inflation adjusted would become $898. Okay? What if we are not talking about power? What if we are not compounding stuff? Well, without compounding stuff, it's pretty easy to calculate. It's actually easier to calculate. Because without compounding, it becomes just $100 times 1 plus whatever the interest rate is, which is 0.05, times the number of years that has passed. Okay? So the first year is identical to the other one, but after 45 years, Okay, keep going, keep going, keep going. There we go. Do you see the difference? Without compounding after 45 years, your $100 would become $325. With compounding, your $100 would become close to $900. I call that pretty significant. Okay? So keep that in mind, okay? The next time you go to a bank and you say, "Oh, I want to, kind of put money into my bank account because I want to save money," keep that in mind, okay? You want to ask people, is that interest compounding? If so, what is the interest? What is the amount of the interest? Okay, after 45 years, what would that become? And so on. Okay, so those are the things that you can think about once you understand, what is the difference between power and just multiplication. But getting back to our example here, okay, so Pat's computer runs at 660,000 times of the speed of my computer. Is that okay? And the boss says, whoever can solve the problem first wins and gets to stay with the company. The other person has to go because that company is downsizing. So do you think I'm at a certain disadvantage here? Okay? All right, so what we'll do is we're going to add we'll add something to this one here, okay? So instead of doing this as a 1, we'll say, how much time does Pat's computer need is going to be, okay, I'm just going to use 1 here because I'm using my computer as a single unit of time. So that will make Pat's computer super fast because Pat's computer is going to take this amount of time to compute, to go through the same computation. Does that make sense? So if confirming one item is not in an array of 1 would take 1 unit of time on my computer, using the same unit, it will only take 1.5 times 10 to the power of -6 unit of time on Pat's computer. So Pat's computer is clearly the winner in this case. Are we good so far? Okay. So now the next question is, what if I bump the size up of the array to 3? We'll work with the easy one first, which is Pat's computer. Remember, Pat is using a linear search algorithm, which means with 3 elements, and what you're looking for is not in the array, Pat's computer or the algorithm is going to say, let me look at the first element. Nope. Second element. Nope. Third element. Nope. Now I have a conclusion that that item is not in the array. So how much time would it take for Pat's computer to finish that computation? It's going to be whatever this number is, right? Times, basically, divided by the factor that we are talking about here, okay? So, and I'm going to change a little bit of thing here, which is just changing the row number with a $sign in this case. It's a spreadsheet thing, but it doesn't really change the meaning, okay? Does that look okay to you, that Pat's computer would take 3 times the amount of time compared to when the array only had 1 element? Yeah? Okay? The battery is gone on this one. Oh, I forgot to give a disclaimer. I am not certified as any kind of financial advisor, so take it with a grain of salt. But I do know about the math side of that stuff. So, okay. So, but how much time do you think my computer is going to take when I have to deal with an array of 3 elements? We talked about that on last Thursday. So with binary search, what is the strategy of binary search? We got 3 elements, right? What is the first element that I'm going to compare to? The one in the middle. Okay, so we are going to compare to the middle one. And I know it's not going to be the same because we have already made the assumption that what we are looking for is not in the array. But what can you do when the middle element is not what you're looking for. You can eliminate 1/2 of the array. So instead of having all 3 elements to look at, now I'm only left with 1. So the binary search algorithm will only need 2 comparisons to confirm that none of the 3 elements in an array is what I'm looking for. Does that make sense? Okay? Yes? No? Okay. All right. So the next number up, remember how we came up with these numbers? It is twice what we have plus 1, right? So the next number is going to be twice of 3 plus 1, which is 7. Okay. So now I can use an equation to express that, which is 2 times whatever is before this cell plus 1, which in this case is 7. And how many comparisons do you think I need? So we have 7 elements to begin with, but if I compare to the middle element, that one single comparison will help me rule out 4 of the 7 elements, which means only 3 is left. It will be 2 plus 1, which is 3 comparisons, okay? So it will take me, okay, in general, just this number plus 1 comparisons to confirm whatever I'm looking for is not in the array. Is that okay? What about Pat's computer? What about Pat's time? It's really just going to be 7 divided by the factor, the speed gain because of Pat is using a newer computer. Is that okay? Is everybody comfortable with reading scientific notation? Sort of? Maybe? Okay. All right, so am I winning? Remember the race is about whose computer come up with the answer of nope, that thing is not in the array first. I'm not winning yet, right? Am I getting closer to winning? No. Okay, doesn't seem that way, right? Okay. So we'll keep doubling, right? Okay, with 15 elements in the array, my computer will take 4 units of time, and Pat's computer is going to take 2.27 times 10 to the power of negative 5 unit of time. So just so that we know how small this number is, okay, for people who do not know how to read scientific notation, this is 0.0000227 unit of time compared to 4 units of time on my computer. Is that okay? So I'm not winning. Doesn't look like that, right? Okay, so we'll keep going. And every time, each row is it is doubling the previous row plus 1 in terms of the array size, okay? What about now? With 65,536 items in the array, I'm still not winning. But do you see a trend? Do you see the increase of my column is increasing at a very slow rate compared to Pat's column? Okay, so we'll keep going until we say, oh, TAC is winning. Okay, and we are getting even closer. And there we go. So when the array has, let's see, when the array has 16,777,215 items, I would edge out Pat's computer by a second. Is that okay? And somebody's going to say, well, that is not fair, TAC. You get to use a computer that is from the 1990s. What about using a computer from the 1980s, making it even slower? Well, I just need the array to be even bigger to catch up. But I will catch up, okay? Why do you think eventually I will catch up? No matter how handicapped my computer is, I will eventually catch up. Unfortunately, this battery is not fully charged because somebody put the battery into the charger with the polarity reversed. Yeah. the charger is not quite foolproof to that point. But it didn't catch fire. Nothing caught on fire. The building is still here. So I guess it is foolproof to a certain point. It's just not foolproof to the point that it can still charge. So we don't really have a choice, for the rest of this lecture. That mic won't be on anymore, but it's still being recorded because it's being recorded using the other wireless mic, which I remember to charge every week with the correct polarity. So there's that. Okay, so what is the whole point of this exercise? What do you think is this whole point? Yep.
I feel like the point of this exercise is showing the binary search engine, like how even though you're outmatched by more processes or how fast the computer is, it still catch up by the way you find information.
Exactly, because the shape of the curve is different. So what we are looking at here is called the time complexity of an algorithm. There was another hand. Let me address that too. There was one more question? No? Okay. So this is important because when you choose a search algorithm, okay, if you choose a slower one, it will be slower eventually. Even if you run a slower algorithm on a super fast computer, eventually it will still run out of steam because of the time complexity being not favorable. On the other hand, if you choose an algorithm that has a much better time complexity, then eventually that algorithm will catch up, even if you run it on a very slow computer. Is that okay? But why do you think that matters to you? I mean, just because text says it is important in the class doesn't mean it is automatically important to you. So how many of you want to become a developer, someone who is going to write software at some point? Okay, we got 2 hands, okay, which is really odd for a class like this, okay? So I'm assuming a lot of people just did not raise their hand, okay? So when you're in a job and your boss tells you, okay, I need you to implement da-da-da-da-da, okay? So let's say we're talking about sorting, okay? Give you an array that is not ordered and you want to make it ordered, sorting algorithms. So most people, including myself, okay, is not going to think about that problem too hard. And then the first thing I'm going to do is to go to Google, right, and look for sorting algorithms. Okay? There's no shame in Googling. No shame in Googling. So I would go to sorting algorithm, and I go to Wikipedia, and I look through all of these things. Okay? You can see there are many, many sorting algorithms. Okay? There's merge sort, there's bubble sort, blah, 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 blah. And some says it's efficient, some says it's simple, and guess what? I don't want to implement something that's too difficult. I want to choose the easy way out, right? So I go to the simple ones and go like, I'm just going to take insertion sort. Okay, I'm not going to open it in one tab. Okay, so insertion sort has its own main article. We'll go to insertion sort as a main article. And there's a little animation of insertion sort. There are all kinds of animations to help you understand how sorting algorithms work. There are even YouTube videos that can show you how sorting algorithms work, and they use Hungarian dancers. Okay, some people caught that. Okay, and I did say Hungarian dancers. Okay, so you just go to YouTube and you say insertion sort Hungarian dance, and you'll find a video where each dancer has a number on him or her, okay, and then they will do the Hungarian dance, and then eventually they will be ordered. It's really fantastic to watch. I'm not really sure about whether it's educational or not, because most people are just focused on the dancing and kind of forgetting about the algorithm or the logic of the algorithm, but it's very entertaining. So this is insertion sort, and what we do is we look at the time complexity of insertion sort. And the best part about Wikipedia is it will tell you what it is. Okay, so in this case, it's here. If you cannot see what it is saying, it says big O, big O in parentheses n squared. Okay, that's the time complexity of the insertion sort algorithm. Then we go back to sorting here, And then we go to efficient sorts this time. We go to merge sort. Okay, we open this up, and here's merge sort. And it has a worst case performance of n times log n. Okay, so somebody who says, who wants to firmly believe in computer science or programming has nothing to do with math, would look at this and go like, math stuff not applicable to me, right? Okay. Instead, that person would go like, I just want to get this done as quickly as possible. So they would look up the sorting algorithm itself, okay? And this is the sorting algorithm of merge sort, okay? Okay, so it's a little bit long and a little bit complex. And they go into insertion sort and look at the algorithm, go like, wow, simple. Okay, I will just copy and paste this code or convert it into the programming language that I need to work with, and I'm done. So, looking from the perspective of the source code, which is basically just the algorithm itself, insertion sort is super simple. Okay, just two loops, one nested within the other one, and you're done. Okay. On the other hand, if you look at merge sort, okay, this is merge sort. You have 3 subroutines, 4 subroutines, and then each one has embedded conditional statements inside the loop and stuff like that. It's like, why do I want to waste my time? I'm just going to implement insertion sort. Okay? What would be the consequence of that decision? It will be slower. Okay? So when the problem size is small, okay, as most test cases will be, you'll be working with smaller test cases because you just want to know whether it works or not. Well, guess what? Insertion sort works. Okay, it will sort the array correctly. Okay, so when the test case is small, you will get the validation. Go like, yep, it works. I don't see what the big problem is. Okay, but as the problem size increases, what happens? The amount of time it takes will basically follow n squared as a curve. Okay, somebody else who spend a little bit more time to study time complexity will look at merge sort, okay, and plot out n log n. And they will find that n log n, even though it's not quite as nice as a linear curve, it is just a little bit worse than a linear curve, but nothing quite as bad as n squared. Okay? So, what is the bottom line? The bottom line is a program that chooses a more efficient algorithm when it actually has to handle real life cases where n becomes larger and larger will become efficient. Okay, it will be a lot better compared to the other sorting algorithm. Is that okay? But how would that affect you as the software engineer or the developer who implements whatever you need to implement and only using one of these algorithms as a tool in your program? How would that impact you as an employee or consultant? Okay, does anyone want to kind of speculate what's going to happen if you choose the slower algorithm? Yep.
It's going to take longer.
It will take longer. And okay, so if it takes longer, it is not necessarily your fault. Okay, so I will describe the other problem a little bit later. What is NP complete? So in this particular case, there are alternative algorithms. So if I choose one that is slower, and then my client is not happy, my boss is not happy, he will go like, Tack, how come the program is taking so long to finish? And then what if another employee comes in and go like, oh, that's because Tack chose the wrong algorithm. And let me show you a faster way to do this. What's going to happen to me and my employment? Not good things, right? Because it has just proven that I do not understand concepts to make a program more efficient. Okay? That is why this stuff relates to you if you want to become a software developer or a software engineer. Now, if you're a math major or an engineering major, and this is the class that you have to take because it's on the list of classes that you have to take, you may not be impacted as much due to time complexity. Okay? So do we have any questions about this discussion up to this point? No questions? Okay. So, but there are times when understanding time complexity will save your job, but in a different way. Okay, so let's just say that you're employed at a pizza shop. Okay, doing pizza delivery. Okay, everybody needs a job to pay for the student loan. Okay, so you're working at a pizza shop, and the pizza shop usually has, pizza deliveries to maybe 3 to 4 stops. Okay, because it doesn't make sense to have like 20 stops on the pizza pizza delivery truck, because by the time you get to the fourth one, the pizza will be cold already. Okay, so you typically have like 3 to 4 stops, and then your boss says, "Well, Tech, I noticed that our drivers do not usually pick, the most sensible and the fastest route to deliver the pizzas to all of those stops. Can you do something about that?" Okay. Well, I suppose I can tell each and every single driver to try out all the possible ways of. Let's say we have 3 stops, okay, A, B, and C. So you have to look at all the permutations of A, B, and C. So you have ABC, AB, ACB, BAC, BCA, CAB, and CBA. So those are all the possible permutations. There are 6 of them, right? So I want each employee to plot out the curve and figure out which route is the fastest. And then the guys are complaining because they're going like, "Oh man, this is a lot of work. I mean, because I have to go to Google Map and look at all the travel time, and it's taking them a lot of time." I go like, "Okay, fine, I'll automate this, right?" So I automate this whole thing. The pizza shop owner is really happy about this, because now all they have to do is to click on a few check boxes of known customers, click, 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 and the program will automatically figure out the order of delivery in order to save the most time, fuel, and money. Great. Okay. 2 months later, I got fired. Why? Because my boss said, "Tech, I trusted you. Okay, but you betray my trust." I go like, "What the hell?" The boss said, "See, the program that you gave me, that can figure out the best route for pizza delivery. When I gave this program to my buddy, it didn't work." I go like, "Well, I mean, that's not possible, because I'm pretty sure the algorithm is correct, and we have already shown that this has worked for months. Okay, I cannot possibly think of a reason why it does not work." So my boss told me a little bit more details, right? And he said, "Well, I gave this program to a friend of mine who's running a courier service, okay? Like Amazon delivery or UPS or FedEx and stuff like that, okay? And the program just hung, okay? I clicked the start button, it never came back. What's wrong with this program? Now I look really stupid in front of my friend because the program doesn't work." Yes?
Wasn't it like originally for like free items?
Say that one more time?
It was like originally for free stops.
Yes. So 3 to 4 stops, depending on, whether those places are close by. So now the question is, so that's a very good question to ask, because then I will ask my boss and say, "Okay, so what is the average number of stops, on a truck like UPS or FedEx? Does anyone know? Just an order of magnitude." Yes? Somewhere between 100 and 200. Okay, so let's call it 50, okay? Because this is a small delivery service. It's only 50. I told my boss, and tell my boss, it's like, this program cannot scale up to 50. Okay, there's just no way it can scale up. Okay, and then the boss says, "Well, that's only because you're stupid." I go like, "I may be stupid, but I dare to say that no one is smart enough to make this program go any faster." Okay, so as it turns out, this is what we call the traveling salesman problem. Okay, if you look up on the internet, it has its own entry in Wikipedia. It's called the traveling salesman problem. And what we are dealing with here is factorial. So let me just show you what factorial plays a part in this discussion. And in the usual manner, I'm going to use a spreadsheet. Okay, so when we only have 1 stop, how many permutations do I have? 1. Okay, so but I am going to be lazy and use the spreadsheet to help me calculate permutation 1. Oh, it has to okay, I just need to use factorial. Okay, factorial of 1. Okay, So when I only have one stop, there's only one way that I can go about doing it, right? Just go there and come back to the shop. Okay, no problem. What if I have two stops? Then I have two ways of doing it because I can say, should I go to A first, then B, or should I go to B first, then A? Right? Those are my only two alternatives. 3, we worked with that already. It is 6, right? So you look at these numbers and go like, well, we can see that it's a little bit increasing a little bit fast, but doesn't seem to be a problem, okay? So let's go to 4. What do you think 4 is going to look like? It's going to be 24, okay? Okay, so it's like, well, I mean, it will take 4 times as much time, but if 3 only takes like a fraction of a second, 4 is going to take, well, a little bit slower, maybe half a second, okay? Not a big deal. What about 50? What do you think 50 factorial is going to look like? Well, we don't have to, we just have to kind of do this, right? I mean, this is the interesting part of a spreadsheet is it will tell you the answer, but it will also tell you how we got there. So if you have 50 stops, then the number of permutations, in other words, different ways of ordering the stops, is 3 times 10 to the power of 64. Okay? If you don't know how to read scientific notation, I'll say in a slightly different way. It is 3 followed by 64 zeros in base 10. Do you think that's a pretty big number? Okay? So that's why the program does not scale up, because the solution to the traveling salesman problem is what we call NP complete. NP complete, I'm not going to say what is NP and why it's called complete, but NP complete means it is a tough problem that up to this point no one can solve in an efficient way. And that would include all the geniuses, okay? All the Stanford professors, all the MIT professors, okay? No one has ever solved any one of these problems in an efficient way, okay? So my boss can fire me, but the chances of being able to hire the next employee and be able to solve this problem in an efficient way is almost 0. So now I can use this point to argue and save my job. It's like, boss, well, this happened to you because you did not ask me about whether this program can scale up or not. Because the solution to this problem simply cannot scale up. Is that okay? So that's the other application of understanding time complexity, is sometimes you can use it to argue with your boss and say, yeah, I know this algorithm or this implementation of a program is really slow, but no one really can make it faster just because of the nature of the problem. Okay? So are we kind of okay with these concepts? Okay? So the bottom line is when you study an algorithm, even if you don't want to get into all the math and the proof and stuff like that, pay attention to the time complexity and understand what it means. Because if you choose the wrong one, it can really impact the performance of a program. Okay? Well, since we have time, one more digression. It has to do with my dissertation or the process of writing my dissertation. I was using Word. Guess which version of Word I was using when I was working on my dissertation? It's Microsoft Word, but which version? 2.0. I was using Microsoft 2.0 to work on my dissertation, and somewhere along the line, it upgraded to Word 6.0. Okay, so what happened to version 3, 4, and 5? No one knows. It's just like Windows 10. What happens to Windows 8 or 9? No one knows. No one knows, right? So numbering with Microsoft sometimes is a little tricky. But anyway, the bottom line is my dissertation only has about 60-something pages, which is really short when it comes to doctoral dissertations. Okay, but it does saving the file got slower and slower and slower and so on. Okay, and it's mostly because I have references from one point to another point. Okay. Read equation blah blah blah, and there's a bookmark on equation blah blah blah, so it has to resolve all of these references. And at a certain point, it just refused to save the file. I click save. After making a whole bunch of changes, it just sat there and sat there and sat there and sat there. Okay? And to the point of, oh, I lost, the content that I just, typed in. That can vary. It's likely to be because of choosing the wrong algorithm on the part of the Microsoft developer. Okay, somebody chose an algorithm that has a very unreasonable worst case performance time complexity, and as the problem size increases linearly, it probably increased the amount of time exponentially to the point that I could not use it. Okay, because I can hardly imagine why a 60-page document it cannot be saved even in the early 90s. So that's another story, another kind of story for you guys to kind of think about, why time complexity is important. Okay, so getting back to binary search. So for the continuing discussion of binary search, we're going to switch back to one of these slides here to take a look at the visual effect of binary search. Okay, so this is one. Okay, there are a few other ones. So if you remember, when we talked about binary search, I gave you several examples. This is one of them, where column A are the values of the elements in the array. 90 is the value that I'm searching for, and then for each comparison, I'm using the correct row to tell you which row I'm comparing to. Okay, do you guys still vaguely remember that example? I hope so. Okay, very good. So when I have 15 of these, then this one becomes the middle one. Okay, I make a comparison. Well, 14 and 90 obviously are not the same, but I can tell a little bit more. I can tell that 14 is less than 90. Why is that less than important? Because the array is sorted. So if the array is sorted, and I know the entry, at row 8 is less than 90, I can now rule out everything before that, because everything before that row is also going to be less than 90. Is that right? Okay. So that means what I have left would be the rest of the array, which is from row 9 all the way to row 15. Does that make sense? So I can now focus on just row 9 to row 15 and say, let's pretend that the array is only this big. Okay, from row 9 to row 15, and I'm still looking for 90, and I ask, well, which one should I compare to next? Whatever is in the middle of the remaining portion, right? So of the remaining portion, the one that is right in the middle is row 12. So I compare to the value of row 12, which is 50. And once again, we confirm that 50 is less than 90, which means row 12 and everything before row 12 can now be ruled out. Is that okay? That's what the graying is for. How many elements do I have left? 3 elements. Okay, we have element 13 to element 15 left. So of the 3, I want to choose to compare to the one in the middle. So that would be row 14. I compare to row 14 and I say, well, 90 is actually less than the value of row 14. So I can now rule out row 14 and every row after that, because the array is sorted. Does that make sense? So now I have only one entry left, which is row 13 itself. And after that comparison, I have now ruled out every single row in the array, or in this particular spreadsheet. And the conclusion is the value that I'm looking for, which is 90, is not anywhere within the array. Okay, so I'm hoping this is kind of reminding you of the stuff that we were doing last Thursday. Yes? Okay. Question?
If the row is like even number,
Hmm?
what do you do if the row is even number, like 60?
Then you have 2 middle elements that you can pick one to compare to. Choose either one. Yep, you can choose the upper one time and choose the lower one the next time. It will still work. Binary search is quite forgiving in that from that perspective. Okay, so now the question is, how do we turn this observation and kind of like a verbal description of how to get it to work into an algorithm, okay? Because remember, in this class, the title of this class is Algorithm Design and Problem Solving, okay? So I'm trying to teach the part of algorithm design. Now that we know this method works, how do we code it into an algorithm? That's the question, okay? So we'll keep this up here, and let me see if I already have a, nope, I do not. Okay, that's okay. I just went past the window that I wanted to use. There we go. So what I'll do next, yeah, we still got time. So is to use a mouse pad, which is just a text editor, and it always opens it in a different place. Let me see where it opened it. Oh, that's because of my watch. The magnet on my watch closes turns off the screen. So let me see, did it open it here? Nope, maybe here, yep. All right. So we'll put it side by side like this, and we can also shrink these columns so that we have a little bit more space. Now, if you had studied before class, you would have known the algorithm already, so this part may not be very exciting for you if you have already read the algorithm of binary search. But if you have not, okay, it's okay. We'll just work on the algorithm step by step. Okay, so when you look at the whole process, column B, column C, column D, and column E, does that look like a loop to you? Does it look like a conditional statement to you? Or does it look like a sequence to you? Are we doing something repeatedly until some condition is met? Or is it just conditional? It's like, oh, if it's like this, go this way. Well, within each column, it is somewhat conditional. But how many times do we have to go through this process? It depends on the number of elements in the array. Okay? It is a loop. Okay? It is a repetitive process. Because we basically have, because you can also think about this the other way. Okay? You can think about this the other way, which is basically saying, what if k equals to 14? What if we're looking for 14? Well, the first comparison will confirm that we got 14 in the array, and we are done. So that tells you that the number of times we have to go through this is variable. It depends on a lot of factors. That tells you that it is a loop. Okay, it's very likely to be a loop. Okay. All right. So we gotta say, we know we are dealing with a loop here, and when do we get out of the loop? Okay, that's the first question you ask is, if we know we're dealing with a loop, we have to say, when are we going to get out of the loop? When do we say we're done? So there are two reasons to be done in this case. What is the first reason? You found the value. Okay, cool. Okay, when k is found in array. Okay, cool. Do we have another reason to get out? If it does not exist. Okay. Okay, k is not in array. Okay. But when you have two things that are both Boolean, this is Boolean, which means it can either be true or false. This also is Boolean, which is either true or false. We need to connect these two using a Boolean operator, and or. Okay. The question is, do you want and, or do you think or makes more sense here? Okay, let's think about what happens when it is and. Okay. Can both of these be true at the same time? Which means the conjunction cannot be true, because in order for conjunction to be true, both sides have to be true at the same time. Okay, so it kind of makes sense for this to be an or, right? Because we just need one of these two to be true in order to get out of the loop. Is that okay? All right, okay. So this is our first iteration of the attempt to write an algorithm. I know it doesn't look like an algorithm, but I mean, we work on this step by step. Okay. So the next thing we want to do is to say, well, let's say we're not just talking about array. Let's give the array a name. Okay. So we'll start to name things. Okay. So k is the value being searched. A is the name of the array. Okay. So this is the second revision. knowing that k is the value being searched, or I should say the key, and a is the name of the array, is there a better way to say that k is found in the array? What would confirm that that k is found in the array? Okay, so k equals to some element in array A, right? Okay, so we don't have I yet, so we can say k equals to a something in A, okay? But the important part here is we have to use the square bracket notation. We cannot compare k to A, because A is an entire array. We can only compare to one of the items in the array. So that's why we need to use the bracket notation, because the bracket notation says, I don't need the entire array. I just need one of the things inside the array based on the expression inside the square bracket, which is going to be a number. Okay? Okay. So that's okay so far. And I really don't have a way to express, when k is not in the array. So we'll kind of leave it alone for a while. Okay, this is our second revision, which is kind of cool. Doesn't go too far, but it's still cool. So now our question is, we probably want to replace the question mark with something, okay? We have used I as the index into an array a lot, okay? So we can use I if we want to, okay? So we can say, I is what we're comparing to, or I selects which element in the array we want to compare to. Are we good so far? Okay, so we want to kind of document that and say what I is. Okay, I is the index of the element to compare to k. Okay, are we good so far? Okay, so we're slowly creating more and more variables to help us express the algorithm. Okay, so at this point, I go like, well, if I is the index of the element to compare to k, according to this picture here, I think we have a fairly good way of figuring out what I should be, right? I is in the middle of the portion of the array that we can say it might be in that portion. Is that okay? Does everybody understand what I mean by that? Okay. So initially, how do I come up with the first value of I? Okay, so that seems reasonable. Okay, so we can say, so we don't know whether it's part of the loop or not. Okay, but we know that I has something to do with, okay, so I has something to do with bar A bar divided by 2. Right? Okay, so it's okay to kind of have that suspicion, and we say, okay, we can take that. But that's not going to work in general, because it might explain how we got I for the first iteration, how we choose row 8 to compare to. But what about the second iteration? How do we choose 12? And the other part is, how do we know that in the last iteration that we would compare to row 13? Because row 13, column E is interesting in a way, because by the time we got to column E, we have one portion of the array ruled out, and then we have another portion of the array ruled out, and what is left is kind of in the middle of the original array. So the question is, how can we remember which part of the array may still contain that value of k? That becomes our question, okay? So let me write it down, okay? So the question is, how do we keep track of which portion of the array may still contain the value of k? That becomes the question. Okay? What do you think? After the first iteration, the array can start from here and it ends over here. After the second comparison, it becomes this. After the third comparison, it becomes just that. So it looks like the beginning. Yeah, go ahead.
Maybe it's bar divided by 2 times 4?
Not quite, because remember, depending on what we are looking for, it can go in the opposite direction too. Okay, So let me go back to the spreadsheet and give you the other examples. Because when we look at the other examples, we'll start to understand, oh, what about this one then? Okay. So if you look at, okay, let me shrink the columns first so it would fit into a smaller space. And then we can look at the algorithm at the same time. So if you look at this particular test case, you will see that, okay, before the first comparison, the entire array may contain the value because I have no idea what is in the array at all, right? After one comparison, I rule out the second half, which means what can potentially contain the array is only this much now, okay? After the second comparison, I only have 3 elements left. But you can see the start and the end of the portion of the array that might contain the value k may not start all the way from the beginning, may not end all the way at the end of the entire array. Is that okay? So that means the portion of the array that may contain the value k we need a variable to remember where it begins and another variable to remember where it can end. Does that make sense? Just based on these observations of several runs of the algorithm. Okay? So what we need in the algorithm is now we also need to say B is the index of the first element that may be k. And I'll use E, one is begin, the other one is end, is the index of the last element that may be k. So combining with these, along with everything that we have already assumed up to this point, let's see if we can refine the algorithm to the point where we know a little bit more about what to do with I, okay? So given these things here, how do you think I can compute I? B is the beginning, E is the end, and I want the one thing that is in the middle. So how do we compute I? Say that again? Okay, somebody mentioned something that sounds right. Okay, where is that? Oh, okay, go ahead. It's the ending. Okay, if you're doing ending minus beginning divided by 2, that would be the offset from the beginning that you need. So you need the beginning to that number in order to get to the index of I, to get to I. The midpoint, yes. How do you calculate the midpoint? When B is the beginning and E is the end. B plus E divided by 2. Okay, very good. Okay. So now we can refine the algorithm and say, oh, we can compute I. It is just the midpoint, which is the index of the first element, index of the last element. Add those two, divided by 2. That would become I. Does that make sense to you? Okay. I mean, if you work up, if you go here and actually do the computation, it will all work out. Because initially, B should be here and E should be here, right? B is 1 and E is 15. How do we get to 8? 1 plus 15 is 16. 16 divided by 2 is 8. Okay. What about this one? How do we figure out that row 4 is the next one we need to compare to? 1 plus 7 is 8. 8 divided by 2 is indeed 4. Okay? And over here, how do we know that we should compare to row 6? 5 plus 7 is 12. 12 divided by 2 is 6. That's how we know. Is that okay? So we plug that into our observation, and we make sure that it does make sense. Okay? It's sensible. But wait, Tech. We did it for every column, not just once. Right? So the calculation of I should not be outside of the loop. It should be inside of the loop, because it is part of the repetitive action that we have to do over and over again. Go ahead.
Oh, that was about
Oh, okay. Very good. So now we know that, okay, this is something that needs to go in the middle. Okay, so cut, paste, there we go. Cool. And guess what? I think we now have a way to find out that k is not in the array. Okay? So just observe, where's B and where's E. B is initially here, and it is now here, right? After the first comparison, B is still here, E is now here. After the first comparison, no, after the second comparison, B is now here, and E is here. Okay? And then after the third comparison, they are the same. Guess what happens after the fourth comparison? So let's try to figure out how B and E changes. Okay, so we are not going to be focused on we won't be focusing on this part here, but instead we'll think about how we update B and E. Okay, and we'll use this example. Initially, before the first comparison, B is all the way up here and E is all the way down here. Now I know the row numbers are off by 1 compared to the array indexes, but it's okay, it will still work. Okay. After the first comparison, which one do we move? Do we move the B or do we move the E? We move the E, we move the end of the array up here. Okay? What do we update it to? Now remember I is 8 in this case, but E becomes 7. So when we update E, we are making it I minus 1. Okay? So we go back to the logic here and we say, do some comparison, but the result of this comparison is I gets E minus 1. So now we want to go back and backfill this condition. It's like, okay, what just happened? Why did we update E from 15 to 7? What just happened? This comparison, right? This comparison is having K being less than A bracket I. Does that make sense? Yep.
Why are we updating I to E minus 1?
Because, oh, you're right. The other way around. Sorry about that. Okay, thank you. So we are updating E to be I minus 1. But why is that minus 1 important? Why not just, say E gets I? Why is it I minus 1?
Because I is the last one.
Because I is, exactly, because A bracket I is confirmed not to be K. So we have to rule that one out as well. So that's the reason why it has to be I minus 1. Okay, that's kind of cool. What about the other comparisons? Okay, in other words, I'm asking, what about after this comparison? What happened? Did I move B or did I move E after the second comparison? We're moving B in that case because the element of row 4 and every element before that cannot be K. So we're moving B in that case. In other words, the index of the first element of the array that may contain that is now row 5. Okay? But what is the decision? What is the condition that led to that action?
E gets assigned to.
It's K being greater than A bracket I. Okay? K is 13. 13 is greater than the element that I is pointing to. Is that okay? Yeah, we got almost a minute left. And how do we update B? It's I plus 1. Very good. Oh, okay. So if you look at this code here, for every iteration, one of these two will change, except when K and A bracket I are the same, right? But that's okay because we'll exit the loop anyway if that happens. Okay? But if A does not equal to if K does not equal to A bracket I, I'm either making E smaller or I'm making B bigger. What is going to happen eventually? They will go over each other. That is the condition that we will be looking for, is to say, oh, it's not there anymore. Okay, there's nothing in the array matches K in that case. So I'm just going to do this one last part when B is greater than E. They can equal. When they equal, you have one element left. Yep. When B is greater than E, that tells you that the K cannot be found in the array. Okay. So we'll stop here today, and then we'll continue from this on Thursday. Okay. So read the notes ahead of me, and we'll continue this discussion.